Welcome to the second half, and I hope others stop enjoying coffee and will join us. And not to keep you waiting, we will start with something that is more future-oriented. Marcelo Melo, who is the chair of the Young Members Group of FIB, so everybody who feels young, please talk to Marcelo. You are always welcome to join. We'll tell you about the work that FIB is doing towards informing the whole community about the practical value of the model code. Yes, so there is an ongoing activity. You will tell more in details and listen, because this is also an invitation to participate. Yes. Okay.
Thank you, Agnieszka. Yes, I will start talking about this example. It's an ongoing activity, as Agnieszka said. We started this task group this year, and we have several working groups. The goal here, we want to translate the principles of the model code into tangible examples, and we need to provide guidance to professionals, enhance understanding and applications of the model code. We want to illustrate the best practices that are in it, address real-world challenges, and offer practical insights for practitioners. We want to ensure relevance and applicability, to ensure that it develops examples relevant, applicable, and adaptable to a variety of concrete examples. So we were asking ourselves, where do we start? So what do we do? How are we going to do this publications on examples? And we found out that FIB, actually CEB, had already this book of examples from the model code of 78. So we found out that these examples were good back then. So we will start from that, and we will evolve we'll start from the beginning. So the first example that we choose was a continuous beam with this section here with a few loadings. So this is a very practical design example, and we started from there, and we want to end up with something like that, a detailed drawing, something that is the job of the practitioner. So we want to start from that and end up in this detailed calculations with every part of how we done and what we do to achieve those rebars and bending moments diagrams and those detailed examples. So so we started the group with this CEB bulletin 1444. We want to create a flow chart as well to help the practitioners to see, I'll start there and I'll end up there, and here's how we're going to do it. So we illustrate the design process. We want to give a step-by-step procedure indicating in each part what is the section on the model code that this equation is, and how you can get the background on that equation. So the work examples can be easily used by practitioners as reference, and the general task group meeting will be held every 3 months. So we have many working groups because model code has many topics. So we created task groups, working groups on many topics of the model code to show the novelties of it. No, not only for general concrete design, but also from many things that they have there. So these are the work groups that we have been created. General design, led by Daniel Miranda, working group on assess of existing structure, which is a novelty of the model code, by Patrick Valery from Switzerland. Design of FRC, Andrea Monserrat from Spain. Embedded FRP from Hungary is led by the Hungarian Sabi, I'll call him. It's recycle aggregate as well from Nikola Tosic. So this is our new things on the model code, but we all wanted to start it with the same example. So every group is doing that same continuous beam and with the same loadings, and we go from there. And this is what the layout that we created to present the detailed calculations. So you can see here, here is where this equation can be found. And this is the detailed equation, and this is the step-by-step calculation. So we'll go very in detail. So people, every time we want to see, do something new, I want to know if someone has done it before and how it was done. Because here we can, well, the model code has many new things. So if you want to only see the equations, maybe we miss some part, maybe we skip some important issue, and in this way I think we can go step by step and help the practitioners worldwide. And also important thing for practitioners, we've seen many things going wrong because of that, to check the units and see if we're using the correct ones. Especially for us in America, sometimes we use ACI, and with imperial units, it's a mess if you don't get it wrong, right. In my country as well, sometimes the technical use tons and the structural use kilonewtons, and we've seen some structural failure because of that. So I think going in details into units is a very important thing. So this is the working group on general design. Here you can see is mainly Brazil and Spain. Daniel Miranda, who is also as a professor and practitioner, so he's experienced with design and also teaches, and he's also involved in Brazilian coding development. Here are some issues that we found when we were looking at the model code on CB examples. They use concrete of 20 megapascals, which is not usually used anymore. Issue with, so we changed that to 325 or 30, which is more conventional nowadays. Reinforcement as well, they use 400 megapascals. We changed it to what we usually use nowadays. Use temperature loading, that's not very usual anymore. To go to an USL, ultimate limit state set, using temperature loading. Also, exposure classes were very different back then. So we using the new update view on that as well. We're using the new class of aggressivity. Also, the combination of actions, the model code goes into detail on it, but sometimes when the model code doesn't go into details, we go to somewhere else, maybe the Eurocode, but we addressing that point on the comment sections on it. So this is one issue that we found, something that we are currently discussing in the working group, because the model code here it has two partial factors for permanent actions, for example. And in the example that we got, we had envelope of permanent actions, which is not really how it's done in practitioner offices. So this is something that we are discussing. So the working flow of this design groupers, we are doing within ourselves, mainly with the young engineers, and then this is going to the people that were responsible on that model code, on that part of the model code. So this will be checked by a senior engineer and outside the group before publications. So this is, they have two partial factors for favor and unfavorable actions, and they are doing, this would be really difficult to be done in practice. So this is something that we are discussing right now. Also, another thing that we found out during our calculations was something odd that we are still debating on how it's if it's correct or not, if it's really it is a special case or it's a general thing. Yeah, was surprised by this. We found that the level of approximation 2B giving more reinforcement than level of approximation 2A. Maybe we are wrong. We will go for checking that the specialists will check that before it's published. But something that we are doing, and we are going to this challenge by using the model code. So maybe something interesting will come out of it. So this nice table that the model code now has, explaining the different levels of approximation for shear, which is really interesting. And we also do SLS for cracking and deflection, and the detailed drawing, and fire resisting for working group 1. This is what I know in most detail because it's one that I'm in. No, the other ones that these are the novelties on the model code. So here you can see only 3 people, 4 now. And so we need more people in those test groups. So if you want to participate, want to be involved, we welcome everyone. So this is led by Patrick, Valerie, and there's 3 people here working on the design examples. And recently, Professor Rob Vergosten from the Netherlands joined, and his group of students are doing separate examples on that and helping with the working group. From March to June of 2025, they are elaborating the design examples on with the help of APFL students, with Patrick, Valerie, and David. They will complete examples by the middle of the year, and will transcript it into the layout that I just showed you. So in this case, for existing structures, instead of level of approximations, they have the level of evaluation for existing structures. So they will go through that levels and the outcome to see the difference between those. So yeah, they mostly using in practice is level 3 and 4. For structural investigation, partial safety factors, and the recommended partial safety factors. So they go through those, and these are the most used in practice, but they are going to compare each level with a performance-based comparison, and also check if it's complying with the Eurocode, the Swiss code, and also the model code. And Professor Rob Vergosten is also looking up into ways to strengthening, with different ways to strengthening existing structures, which is also sometimes the case. So they are using the old example from CEB and checking for current standards and the way of assessment. So this is what they are doing on the existing structures. This is the working group for design fiber reinforcement concrete. A lot of people from Politecnica de Madrid are on that group. So Albert de la Fonte asked all his students to come forward, and they are helping a lot with it. But also people from the United Kingdom, Italy, and so you see it's a very diverse and international group. The issues to be addressed in the model code, they use old materials that are not used anymore. So in this case, they will do with the model code concrete with 40 megapascals, reinforcement with 500 megapascals, and FRC class 3C, and also a different exposure category. The approach, what they are looking for, they are going through ULS, SLS, serviceability condition on limited states associated with FRC structures, and also something that it is going forward. It's not done yet, but they are going to go to numerical analysis as well, and sustainability assessment, which is really a new thing that you can find in any other code. Yeah. And also the embedded AFI fiber concrete reinforcement. Many things are related to what Professor Georgi just mentioned. So Shabi Znvai from Budapest. Also from Hungary, you have Somali, and Motohiro On from Japan. Yes, they are also working together. They already designed the flow chart. So we want this to be done for every working group, which is really nice. So people go step by step, saying like, am I doing it right? What's the next step? This is a great thing for practitioners. It would be lovely to have that on every aspect of model code. So they are modifying to fit the model code. Which fiber reinforcement product they are going to do the example. That is the discussion that they are having. They will probably use glass FRP, which is widely available, and most of working members have experience in. So maybe we need some more contributions in the future about other type of reinforcement. So they want to focus on the creep phenomenon, where can tensile strength can be utilized, and also, as Professor Ballas just mentioned, the lack of yielding plateau on FRP, the constitutive behavior. The methods associated with plastic analysis and moment distributions are not observed. Slight higher tensile strength they need for regular reinforcement, but on deformation capacity, they had to limit the compression zone, and this is a case for ductility. Sorry, you understand. Yeah. So to have sufficient aggregate interlock, it's because of bending of the fiber reinforcement, they reduce the strength of the FRP a lot. So this is the case that Georgie just mentioned, and it's going to be addressed also in these examples with the numerical part of it. And yeah, this is it from their side. Also, they are going to check for serviceability. The stiffness of the rebar might be significantly lower than the steel rebars. But we're going to check and compare, because we are going to have the same examples on regular reinforcement and with FRP. It's not a case to see who is better. Each case applies to a different kind of solution. So not a case to compare how it costs, how bad, who performs better. It's just a way of, this material has this benefit, this material has this benefit, and we're going to show the calculations, right? This is the last working group, led by Nicola Tosic from Polytechnic University of Catalonia. This group also is very diverse, people from Australia, Spain, Netherlands. Also Agnieszka is involved on that SAS group as well, on this working group too. This group has a difficult meeting because of the time differences, but they are working on it. So this is what they want to do, to establish the parameters that they vary in the first examples, because recycle aggregates can vary a lot. They have many parameters that they can choose and will change the results. So that they worked was divided by the members in this first stage, and they are using many parameters for the interlock and bonding as well. So this is what they are doing so far. This is an ongoing project, as I said, that we count on that a lot to help practitioners in the future. This is what I had to say. So I would like to thank you very much for listening, and also welcome new members to join. You can join the FIB page and help us with your knowledge and expertise. All right? Thank you. Thank you very much.
To what you were saying, this is you are welcome to participate in these examples, but the project is expandable, yes? So we can also add another cases to the scope. We have not yet covered all the innovations, and and also the type of the example can be changed. So if you are interested, if you want to learn from that exercise together with young members, Marcelo can be found on...
Yes, we just, during this conference, we're starting a new working group on bridges as well, right? So in this near future. So,
exactly. Seismic is also still an open field where you can raise your hand and even take a lead. This is a learning project for young people, but this is also a very powerful means of disseminating our knowledge to practitioners. So that's a very serious point. And yes, and one of the questions Marcelo has pointed out as something you work on is a dilemma about levels of approximation in shear design and what kind of outcomes they lead. And therefore the next presenter, which is Steve Foster, will tell you more about innovation in shear design in the Model Code 2020.
Need to acknowledge that the bulk of this was put together by Aurelio Mattoni. I've added some additional material, particularly around the fibre reinforced. But just a little bit of the history of this shear. So back before Model Code 2010, around about 2009, 10, Model Code 2010, remember it's published in 2013, Aurelio came to talk to me. I was chair of Commission 2 at that time and leading this group, and he came and had to me and said, look, we really need to do something about shear. The model's very empirical. There was a lot of... Shear was one of these things that was really controversial, even though we were designing it for a long time. And we had to convince Just Walraven that we needed to change it. And Just, also an expert in shear himself, with a very significant view in one camp, and that was the Sooty equation, very supportive. Took this on and said, yes, we need to look at shear, and which we did. And in 2010, the model code got changed to some extent, and it got further refined and updated in this last model code to be much more consistent. Just a few things we look to trying to get the new provisions to make sure that we had consistency. Had to update for any new findings that we found since 2010. Update on the ductility class, which is a big debate. Was a huge debate in Australia going back 10 years or so ago. To try and avoid these difficulties around levels of approximation. You saw one, Marcelo, just a minute ago when you look at these, and I'll explain why we get these different numbers there. And then look for this one's particularly a more consistent way of modelling those directly supports. Some people like the strain-based, some people for closed form solutions, but they come back from the same theory and model. And again, this comes down to how you work in a consensus forums, and then to look at the statistical data for assessment of existing structures. There's quite a lot in there. I won't go into that in great depth, but assessment of existing structures, particularly got non-compliant detailing in the code, so it talks about how you deal with those, and then just look for higher guidance on nonlinear analysis and the like. All right, so level 1 equations are really derived from the higher level 2, level 2 derived from the higher level 3. Now, ideally, what you would have is you would have one consistent formulation, which is your highest level equations. You would then simplify those down with some restrictions parameters, so that's your level 2, and you might have simpler versions of that. So if I'm doing a new design and shear is not going to be critical, I don't need to go do the very high level calculations. I've just got to justify it using the lowest. It's just really usually a nice simple formula. But we want to do higher levels when you've got assessment of an existing structure, right? Particularly if you've got non-compliant detailing. We don't want to start tearing down structures just because of that. So in those cases, we may want to put more energy into and go to higher level of approximation, or even to numerical modelling. Right. So one of the things, because of the way that we deal things, and this is put in because there's a lot of people that go and take the level of one equation and put it against the data plot and say, oh, look, see, it doesn't work very well. No, of course, when you misanalyse something, it won't work very well. So remembering the level 1 doesn't take into account the strain in the reinforcing steel and the strain in the steel. So you get a number, and you know that number is going to be conservative against the level 3. But if the strain, say the mid-height strain is at about 0.001, you'll get a much closer realistic answer than if it's 0.005 or 0.015, right? The level 1 approximation assumes the longitudinal steel has yielded. Right, that's the most conservative case. It's controlled by flexure. In most cases, our shear sections that are critical are not co-located with our flexural sections. It can be in negative, when you've got negative moment regions, but if you've got positive moment regions, right, the shear is due from the face of the support. The flexural governing zone is at the mid-span. The strain, your mid-height, is not yielded. All right, so we went to strain-based approaches. This is essentially, it's the modified compression field theory that was built up by Michael Collins and his colleagues, and you'll see here that this here's the strain. And I'm not going through that, I'm assuming most people will be familiar with the modified compression field theory and the mid-height strain parameter. I will say, though, that the mid-height strain parameter is actually there for a crack width, right? It's dictating what the width of the crack is. The width of the crack dictates how much aggregate lock you get, how much friction you get. So everything can trace back to a crack width. And that becomes important when we start to add in steel fibres. Europe recently updated their Euro codes, and you'll see that they don't use a strain-based approach. They use an equation here, which interestingly, and I can only relay stories because I wasn't at the table, but people are uncomfortable when they change an equation that doesn't look like Zulti's equation. So the equation is manipulated to look like the old shear equation, so you've got this power to the 1/3, even the A and the D, this, but when you dive down much deeper, the A here is not the shear span, it's something completely different. This is an aggregate size effect, it's a square root, so the equation actually isn't anything like the Zulti's equation. It's a curve fit to the strain-based equations that assume that the steels are yielded. Right? So it's a simplification, but it's consistent with the theory. All right? And that's okay, and the details are given on that. So again, we have these 3 or 4 methods of approximation, but we have a hangover, these 2 level 2 approximations. This is because when you're, again, looking at committees and consensus, different people have different views. One of the models, the way, if you look back to Model Code 1990, for example, it's all based around plasticity models. And those plasticity models are fantastic. They work really well. Some people still want those plasticity approaches, and that's what you got here, because the approach is different to that for a strain-based approach. So how do you build in the plasticity model to make it consistent with the modified compression field model? The modified compression field model has a concrete term, right, a VC term. The plasticity does not. And the way this is done historically is you have a database of tests and you refine your model parameters. In the plasticity model, what that you found is they used flatter angles of theta, so flatter shear angles. So you still get the same calibration. Of course, you've got a flatter angle. It means your steel becomes more efficient. You've got more steel reinforcement. In the old models, 3600 ACI, steeper angles, you've got less steel. So the numbers add up to the same, but you've got a more efficient steel and no concrete. The other one, you have concrete component and you have less steel component. So this is where it gets into trouble now, where we get these 1 and 2. And Marcelo, it doesn't surprise, it probably surprised me the level of change, but it doesn't surprise me you get different numbers. But what I would very much hope is none of them, neither 2A or 2B, are giving you less conservative answers than 1 or more conservative answers than 3. So that's the reason why the 2A is based on the stress field and 2B is based on compression field theory. There was a lot of work, again, the background of this is in Sigrist. I might add that in the initial work, Victor Sigrist led the team. It was essentially him, myself, Aurelio, Matoni, Evan Bentz, a couple others. In the second term, was Aurelio Matoni led the team. So this is the area here, and you can see the different curves. This is the curve that was in the Model Code 2010 for strain X based on a theta. And you'll see this has been refined and updated, trying to bring these plasticity models and the modified compression models closer together. So we have less inconsistency in them. It also takes into account the level of ductility in the reinforcement. So if you've got a ductility level B, or in Australia, I think in New Zealand we call ductility N grade, you have a value. If you're going to use a lower ductility steel, you'll see here you've got a different value for your minimum theta. And this is to take into account the lesser capacity for redistribution on these steels. But if you've got a C or D class steel, you've got a lower value of B, because again you've got more ductility, more chances for the steel to become, or the cracks to rotate and the steel to become engaged. All right, and this is simply it. You know, if you've got a B, you can reduce from our standard by 10%. You've got ductility C or D. That would be E class in New Zealand. You can reduce the amount of minimum stirrups by 20%. And this is something I think we'll reflect in them later. We come to add steel fibres, and I note here, so this is the area here. Of course, everything is tied to crack width. So the reinforcing steel is also tied to crack widths, the concrete component and the steel component. And the reason this steel is tied to crack width, because as you see here, as you get the crack widths going up, you actually get a slight decrease in the steel component, right? The steel's yielded as plastic hasn't changed. So what is changing? Well, it's the strut angle, right? So the strut angle is a function of the strain. And if the strut angle is, as you go up with higher crack width, is decreasing, so increasing, you've got a higher strut angle, the steel component actually slightly decreases. So all three are combined there, and because of crack width, we're going to get a consistent approach. One thing to note, so plasticity has this, the movement is downwards, and the movement of that crack opening, which defines the crack width, fibres align with the direction of movement. They're very flexible, and they more or less, the stress aligns with the direction, not normal to the directions you'll see on many people, many papers. So this is the equations for a member without shear reinforcement. So again, it's nice and simple. It's the same equation for the concrete component. We add in a steel fibres component, and this is given by here. You'll see we've got a strain factor here. It's the same strain factor. It's consistent. The same angle for theta is consistent, and then we've got a crack width. And if you go back to the very early things of modified compression field theory, they have that crack width equation in there. It's a nice simple equation. It's this, 0.2 plus 1,000 times epsilon x, and this is because we've got a strain effect. This is one thing that changed between the 2010 model and the 2020 model. So in the 2010, this was on the left-hand side. It was fairly new theory at the time, and we didn't have the strain effect for uncracked sections on that. The rest is the same. And you get this, depending on what your ultimate crack width is going to be, where you typically take 1.5 millimetres, you get a stress from your constitutive model, and the rest you plug in. Same with shear resistance when you've got steel. Again, you can just add the steel component because the steel's plastic. The fibres decrease in strength as you go up in crack width. So again, this is solvable if you decide on what that crack width is going to be, 1.5 millimetres, for example, then that gets fixed and so on. So from a design perspective, it's fairly easy. If you're analysing an existing section, you've got to do it iteratively because these things will change. But the iteration's not that complex. All right, now the next one here is a better treatment of how loads are taken directly to a support. Again, this is trying to amalgamate the theorems so we get a consistent approach. And you'll see here you've got two components here. You've got the shear carried by the reinforcement, you've got the shear carried by the direct strutting, and what you've got in here is a strain term, KE. I haven't given you the equation, but as KE, as the strut flattens, that goes down, and that term reduces. So we get a consistent model then with the strain-based effects models. All right, I'm not going to go through on this in detail because I just notice I'm running out of time. But again, for the punching shear provisions, there have been some updates on that to take into account the benefit of membrane actions for internal slabs. So that's the main change. So you had that hidden safety factor there. So similar thing, it's a strain-based equation, and we're pretty close now that when you take the two-dimensional equation and you extend it out so it becomes one-dimensional like the boundaries, you get similar results. Right? So we're getting closer to a consistent uniform theory between two-dimensional problems and one-dimensional problems. And again, this is based on Mattoni's critical crack theory, which forms the basis of this. Now, just this last slide, it was an example of Aurelio's where they had to look at a parking structure, a real structure, and again, assess its current capacity. Without going into too much depth, this is essentially the load path here. If you use the lowest level of approximation, in the case approximation 2, you get a result here of a bit under 3,000 kilonewtons for its capacity. If you go to the higher level and include the membrane action, we're getting pretty close to the optimal. And then if you go to a higher level again, you get the most optimal. So this is really important for assessment. So if you take this structure and says, well, do we have to upgrade it or do we not have to upgrade? Do we have to spend money on it or not? You can see with these tools, it can change your decision or change the amount of retrofitting you have to do. I think, Agnieszka, that's me done. Thank you.
About shear, we probably would need like 2.5 hours. So the lunch break will be good to talk to Steve, and then we will continue until the dinner time. So that's thank you so much. We will go back to assessment again, and this comment of Steve that it's, some of this level of approximation are very relevant when we go into the assessment, where we will be listening to the presentation of Alberto Meda later on. But first, we start with reflection of seismic, yes? Alessandro, yes? Unless you prefer to swap, but no, okay. And again, I suppose we will need some help. As I told in the introduction, we had this ambition in Model Code to cover different actions. So also cyclic loading and seismic in particular. And very relevant here, but we are also aware that there are different approaches and different ways of doing it. So here probably you will take us inside and out for the Model Code. Yes?
Yes and no, I would say. So thank you, Agnieszka, and good afternoon. I think we are after 12, everyone. So first of all, apologies, I'm not very energetic today because I didn't sleep, so I may even faint during the presentation. So, but what I will try to do is actually what I did. I was actually not part of the group that developed the seismic part in the Model Code 2020. So I tried actually to read it and give my perspective as a researcher, but also as a designer. And so the main component, it's really the part related to the is 30.2 tree. And as you can see, there are different components. Now, we will talk about these. I mean, you will have the seismic action effects, the cyclic plastic rotation capacity, the component valve verification, and then there is also special provision about low damage design. So, but in this section, the focus is more on the capacity side. So therefore, there is not much in terms of design methodology to determine the demand on the structure. And then also there are parts which are, let's say, material agnostic, like seismic isolation, no structural components, and foundation issues that they are not covered. Although we may argue about that, right? Because, for example, no structural components, the way you connect the non-structural elements to the main lateral load, that is actually very important. It can change the failure mechanism of the lateral load system. The other thing is that that part, the model code, is a performance-based, and they call it displacement-based. And I put the brackets here because I know, especially the New Zealand audience, when I talk about displacement-based, you think about displacement-based design introduced by Professor Nigel Priestley. But in the way is conceived in the model code is slightly different. But it's still talking about displacement, which is a good thing. And then obviously the model code has a probabilistic basis, and so is also, we have to remember that most of the formulation relies on the partial safety factors on the material, while in New Zealand we tend to follow more the ACI approach where we have one partial factor. So in terms of performance level, there are the four performance level: operation, immediate occupancy, life safety, collapse prevention. These are the hazards levels. You go from frequent earthquake with the return period association up to very rare. And obviously with these, then there is associated the damage and the operation of the facility. And this is, I would say, we may argue about the, what could be the probability of accidents or the type of damage, but I would say that more or less this is quite in line even with the New Zealand standards. I would say even with Caltrans, although now they are changing a little bit the performance limit states. But I think what is important, and when I was going through the document around 3 a.m., trying to do my best, I think it's important to recognize that in that part, when you read, there is not much about forces. That's why it's called displacement-based. You will see there are many formulas, and I will show you something about rotational chord. So, and you will see a lot of formulas that will be applied for different cases, but the concept is that you need to look at displacement and not at forces. Of course, then the way you estimate the demand could be done in different ways. And so you can have a traditional elastic approach, quasi-static approach. You can do a spectrum, multimodal spectrum analysis, or then you can do a capacity spectrum analysis, or you could do the true displacement-based design. The idea here is that controlling and looking at displacement, obviously, and understanding from the yielding up to the failure, you can have a better understanding on how the structure is going to perform during an earthquake event. I have to tell, especially the FIB Presidium, that the New Zealanders are very, very well trained about displacement. I know when we used to teach, even at the University of Canterbury, we had a lot of labs where I'm actually teaching them displacement compatibility and so on. So maybe for the New Zealanders, it's actually very boring what I'm saying, so apologies for that. It looks like a lecture that I'm doing, I was used to do in the class. But what I want to highlight, for example, which is not in the which is not in the model code, is actually that, for example, one of the main bases of the displacement-based design introduced by Professor Nigel Priestley is that we don't really talk about secant stiffness, but we actually talk about yielding curvature. And basically, by his analysis, we're actually showing that if you change the reinforcement on the, and you do a moment curvature, you change the reinforcement of the section, and even in a certain range level of the axial load, then the curvature, the yielding curvature, is the parameter that doesn't change. And then he was able also to correlate that with the geometry, so the mechanical property, the yielding of the bar that you define as a designer, and the section, the main section of the pier of the wall that you are considering in the seismic direction. So the other key thing is that you may be familiar is that when you look at the true displacement-based design, you start from the displacement as a design parameter, while in the model code, the displacement is more a check because most of the methods are still referring to a force-based approach. And I don't want to go through, but this is step one. You define the displacement. If it's multi-degree, you have a critical displacement in the member, in the critical member. Usually is where you expect to have the higher displacement demand. And then you have a way to turn it in a single degree of freedom. You go into the damping ratios versus displacement ductility, because we know through the curvature, the yielding curvature, we can calculate the yielding displacement. We define the target displacement as a design parameter. We know the ductility. Then we know the equivalent viscous damping. We'll go into elastic spectrum, which are adapted with the equivalent viscous damping. If, for example, we have 20%, we enter the 20% with the displacement that we define with the design, and we get the secant period, which then will give us the secant period. We can calculate the secant stiffness, which will give us the force at the target displacement will be adopted. So, and this is different from what is in the model code, but is another approach which has the merit to use the displacement, which are actually our damage indicator in the structure, as a design parameter and not as a check. In terms of seismic analysis, I probably will skip this one very quickly because it's very brief. There is a brief paragraph in that section, and as I was saying before, the type of analysis that you use is important, is relevant, and is related to the demand, and that will then allow you to calculate the capacity of your members. But usually what happens is that you tend to define elastoplastic, if your critical member, your fuse, you tend to define an elastoplastic moment rotation, right? In this case, you will have to define, obviously, the secant stiffness, and then you will have the yielding rotation, the maximum moment, the ultimate moment, and then that is defined when you have a drop of 20% of the capacity. Now, what we will see, and this is actually in the model code, you will see that, as I was saying before, the key parameter is the rotational chord. In the rotational chord, you will see that you will have the ability to calculate the rotational chord at yielding, but also at ultimate limit state. What can we say? I would say that by reading it again, most of those formulas, there are physics-based models, but most of those formulas are empirical. So I will show you later. Are based on a set of database which has been collected and then they've done the fitting on with the model that is being calibrated in the regression analysis. If you have, while reading the document, if, for example, you have an assessment on existing structure, the recommendation is always to try to calculate the secant stiffness by looking at the moment curvature and possibly average the positive and negative, instead of using maybe formulas which are, again, could be empirical formula that maybe has been validated on new structures, and they may have a far higher variability. Now, the database has been over 400,000 tests. Unfortunately, I didn't have time to dig into the database, because that is quite important, and even understanding what are the sources of the database. But the idea is that within the database, then, in the model code, in that part, you can basically cover, there is enough material to cover conforming rebars, then non-conforming means possibly even with lap splices in the plastic hinge, something that in our, unless they change it, I don't think so. In the New Zealand standard, we are not allowed to have any lap splices in the plastic hinge. And then we have also information about FRP jacketing, again, with lap splice or without lap splice. So, and then also data for what related cyclic shear resistance. So, you're quite familiar with a regression analysis. It's like I would say the first way of calling machine learning is one technique of machine learning, right? So regression analysis, and this is typically what has been done in most of those formulations. There were a set of data, and then the model has been calibrated in order to have a perfect fit with the experiments. In general, the section, the most important part, which is related to the rotational code, I would say, in general, you have the three main components of the fractional, the shear deformation, and the fixed rotation in case you have slippage. And that is very important, especially if you have an existing structure where you may expect that the development length has not been properly analyzed, or especially if the structure was designed without seismic codes. Therefore, you may have that contribution. It's quite important because it's increasing the deformability of your structure. And these are the three components. There are different cases. I mean, you can have a scenario where you can even trigger the shear. Obviously, this is a very slender column, means that in that case will be that you don't have enough stirrups, and that is probably more the case where you have to consider an existing structure. And here there is the contribution of the slip, which is very similar to what we have. You guys probably are familiar. If you think about the rocking structure, it's pretty much, it looks like a big crack development. Here you have the bond, losing the bond, so basically they will in the slip, and this develop a big crack, and therefore sort of activate a sort of rocking mechanism. In terms of failure, again, the approach has been to provide that there is the analytical formulation, but then, especially in scenarios where you have the slippage of the bar, that becomes more difficult to quantify. There is this extra contribution, means that you start having the slipping of the bar, the slippage of the bar, especially for existing bars, and it may progress further beyond the yielding, so you want to compute that also in the contribution of the plastic hinge. And so you will see, I decided not to put all the equations because they're very long, but I decided to, basically, the message I'm sending you is that basically you have those imperial equations trying to cover all the possible spectrum of applications for existing and the new design. think I want to go a little bit faster because I'm running out of time. And this is an example again of, in this case, that you can see with read bars that are formal data. When if you look at left splice read bar, you have far less. So that has always to trigger you a bell, right? Because remember that these are empirical formulation. And in terms of shear, I'm glad that Stephen has covered that. Shear, I think, for the New Zealanders, I recommend to really strongly, more than any other topic, read the bulletins because it's the most researched topic in the FIB, I think, right? David can confirm. And I have to say it's pretty advanced. And in fact, what I liked, we are quite familiar because being from New Zealand, Nigel Priestley developed the UCSD, university where now I'm from, a model where you have a decay of the shear with the increase of the ductility, which is quite normal, right? You start increasing the strain in the bar, you lose the aggregate interlock. And what happens is that the problem is that if you don't have enough capacity protection, then what happens, you will start having the intersection with the flexural capacity. And that basically means that, as you can see, those hystereses, you start having a drop in displacement capacity. And so, as Steve was saying, these two terms, these and these, they're both dependent on the strain, which is dependent on the curvature, which is then dependent on the ductility, right? Because as soon as you keep increasing the strain, means they will increase the ductility. But this is the one which is really making the most contribution because this is the inverse. I didn't put it in the slide, but it goes with the inverse of the strain, which basically makes the shear capacity dropping. And there are other parts that have been in that section. I found this one very left very open to the designer in the sense that, for example, this in one sentence, it is lateral stiffness strength of secondary area may be neglected in the model if the effect is favorable. Then if I ask you, when is favorable the effect? People that maybe they don't have a strong background in earthquakes may say, oh, if I have a masonry in field, it's actually, my joints are well protected, is actually increasing the strength, so maybe I should include it in the analysis, right? But if I have a displacement approach and I start thinking that can affect the failure mechanism, that it will not be certainly acceptable. So it's very open, and I think in New Zealand we have a little bit more strict, but that could actually, from my point of view, could create maybe some misunderstanding, especially if you don't have highly competent earthquake engineering background. And the fun part is the last part, because it's the resilience, the true resilience. And I'm very glad that has been put that. It's basically work that has been done by Stefano Company, who was at University of Canberra, myself, and by the New Zealand Association, Concrete Association, where at the time there was Bob Park, who was actually leading the standards. But what are the downside? This work has been done 15 years ago, right? And what we have there is pretty much all the finding that we had from the PRESS program developed by Nigel Priestley. This is a test that I did 10 years ago on a bridge pier where we were simulating cyclic loading accelerated, and we've made far more progress in there. Right now we have armoring of the bottom part. We use the dissipative fuses, which has external. We have different ways of preventing shear failure with mechanical shear hinging, and we have traditional axial devices, or we have U-flexural plate. So I have a 3D printed model of the device. If you want to have a look, you can pass it on. And this is actually a Japanese from Sumitomo Electrics. He gave me these because it's quite interesting. You can use this as a recentering, right? Because usually these systems have a post-tension in the recenter. But the beauty of this is also that it has fiber optics embedded. So why I'm saying that? Maybe I can pass it. And this is the toy. This is a pre-stress structure, right? And then if you lose pre-stressing, these are when they do teamwork. So we don't have to lose pre-stressing in those type of systems. Otherwise, we don't have resilience and we don't have recentering. So there are a few parts that in that section, which is I think is very high level, are missing. The recentering ratio, the monolithic beam analogy has to be adapted, the detailing, the capacity protection of the members. We made further improvements. And to me, we need to start, because we talk about resilience, we need to connect this to the recovery function, repairability. I don't know if I show you, maybe, let me see, here. So I tested the same structure with a emulative cast in place, the traditional plastic engine. This is the Toyota, right? And this is the Ferrari, right? I like Toyota though, I have a Toyota, you know that. I can't afford the Ferrari. So, but what happened after the earthquake? You have the damage here, you have nothing here. Now, when we talk about resilience in earthquake engineering, we talk about functionality, ability to recover after an earthquake, right? So, what will happen? Most likely we will have to replace only the devices. But if you also design carefully the devices, or you depend, if you use a viscous damper, for example, you may not even to replace the devices. The other thing is that if we have monitoring on the devices, we can even know exactly what is the strain demand, and therefore we can even be, if the earthquake level is not producing high strains, we can even simply say we are 100%. But you can see then these, the red, the Ferrari, the recovery time is far shorter, the drop is far lower, therefore the area, the R factor, the resilience factor gets better. So I think we have a bridge tonight. There is 23 Japanese experts, world experts. I'm going to see the bridge. I worked together with WSP and the Christchurch City Council. And I just want to mention that there has been a lot of work has been done. It's not been done within the commissions, right, or within the tasks. And therefore, I think it would be good to make sure that to bring people to have them working on this. And then there is also a guideline. I think Mustafa is here. It's been sponsored by NZTA, Kotai, and Concrete New Zealand. They will be out, I don't know, Mustafa? Early next year, so it will be available for everyone, and so you're more than welcome to use it for free. All right. I think you got the takeaways. I went a little bit longer. So the only point I want to make, when you have empirical formulation, I'm not against empirical formulation, but it's important that you know the sources where the data comes from. And so for New Zealand, we have different detailing. It may be that these formulas are not tailored for the type of structure that we have. Thank you very much.
Thank you, Alessandro. And this is exactly the type of reflection that we need, because as we said, the work on standardization is based on the understanding and not the knowledge. Global Association SSFIB should benefit from the global development of knowledge. So everything will be passed through. You know how it works. Join the effort, and then everything will be even better than it is now. And since we are here, again, very impressive the level of understanding that you have developed here for good reasons, and joint effort to make it available to others. Alessandro, Mustafa, and a lot of New Zealand colleagues, I think we can learn from you. And now we will move to assessment, because that's, well, you already mentioned, Alessandro, design and assessment go hand in hand in seismic, but also in, with regard to deterioration and damage. Alberto.
Yes. Okay, thank you. Okay, I would like to explain how we reach this part of model code on existing structure, because I think that moving from model code 2010 to 2020, one of the most important novelty is considering existing structures. And also the idea to have only one code that cover new structure and existing structure. We start a lot of discussion in FIB. We start to create a special activity group in 2009. At the end, we developed some work. The first idea was to have a separate model code for existing structure to the new one. At the end, as a long discussion in Technical Council in 2016, we decided to have a uniform code that cover all these aspects. And I think that was a good idea, personally. And we have the model code, but we have a lot of other products that could help people that are going to assess the existing structure. And particularly, there are bulletin, starting from bulletin 80, that is the partial factor method for existing structure, and other model that in a way, I'll point out about the model 111, because I'll show something about this bulletin that is modeling structural performance of existing structure. So that are a compendium to the use of Model Code 2020. And we know as designer that in the life of the structure, there is some point that we have to perform, you have to make a performance evaluation of the structure, a performance assessment of the structure. And so there are a lot of reasons. The age of structure that are designed with old codes, load selling could increase, degradation of material, damage occurred, and so on. So we have to approach to a performance assessment of structure, and in model code we have that information. We have a lot of parts related to existing structure in model code. I will focus only on two aspects that are, for me, important. One is the use of partial factor for existing structure, and the other is the degradation of material, in particular degradation of reinforcement, because I think that is one of, on my reason, one of the most new aspects. Regarding partial factor, in the introduction, Agnieszka told about the possibility of using a beta value that is lower for an existing structure, but it's not only this, because we have a different knowledge of the structure. We have different uncertainties in existing structure respect to the new one, and that we could take into account. For example, that are the partial factor suggested in model code for the permanent load. You can see that are the self-weight, the coefficient related to the self-weight load, and this is for the other permanent load. And if you go to the existing structure, there are two different approaches to having assessment. One is to verify the need of safety measurement of our structure, or if we have assessed for an upgrading a structure. In that way, we can use different factors. And in particular, if you can see here, for example, for the assessment of the structure, we can have two different values related to having self-weight or the other permanent load. But also, we can divide, because we can have different knowledge about for example, the self-weight. Because in existing structure, we can verify the density of the structure, we can verify the geometry of the structure. So if we have deeper knowledge, for example, on geometry, we have deeper knowledge on the load, and so we can reduce the factor. And so it's the same for the effect of other design action as imposed loads, no load, wind load, and so on. And we have this is for new structure. This still is for the assessment and verify the need of safety measurement and for upgrading the structure. And also with the material, the GAM-M, in which we divide the characteristic value of the strength, we can have different approaches. That is for new structure, GAM-C for the concrete, GAM-S for the steel. And still, for example, you know that when we define the GAM-S for the steel, we have several uncertainties inside, particularly for the position of the reinforcement, the detail of the reinforcement. And it's clear that this is for new structure. We can have different GAM-S related to the knowledge that we have, the quality control that we have, and so the different dispersion and detailing of our structure mainly is the actual depth of the beam. And for existing structure, still we can have this knowledge, particularly, for example, for the steel, we can really measure the geometry of the reinforcement, so we can reduce the GAM-S, because we have different uncertainties that are usually covered in the partial factor. Now I move to another important part, that is the reinforcing steel in existing structure. We can consider mainly two situations: reinforcing steel without deterioration and reinforcing steel with deterioration due to corrosion. In reinforcing steel without the deterioration, I would like only to point you something that is clarified in Bulletin 111, particularly that we have two possibilities of classify the steel, I mean by strength, that is the actual strength we can measure on the structure, taking some sample and test it, and the other is to use the nominal strength for which the structure was designed. That is very important, because sometimes if we have to perform tests on the steel, we have to take bars. We have to take bars for every type of steel used in a structure, particularly for every diameter. So that is very probably in some times is very difficult. The alternative solution is to use the nominal strength, meaning strength and size strength and ultimate strain, that are which information could be gathered by the original design, the own calculation, former design code, and test on limited number of bars. And particularly, for example, in Bulletin 118, there is the different characteristic of the steel that is for in Germany, and we can have for different age of the structure, we can have this information about the steel that was used, and we're using the nominal strength, so with limited number of tests. We have this, that was in Bulletin 83, but for example, in Italy, we have similar frame that allow us to, when we know the age of the structure, to know, to have an evaluation of this. That is simple, but was, I think, clarified in the code. Another aspect is the deterioration. Corrosion. In some previous analysis that the practitioners used, they considered the corrosion only as a reduction of the area of the steel rebars. And that could lead to very wrong, to link to some mistakes. Because when we have a corrosion, we have not only a reduction of the cross-sectional area of the reinforcement, but we have also could have a strong reduction in ductility of the steel. And Alessandro presented now before the problem of ductility. And we think in a section that if we reduce the area of the steel, we have an increased ductility, because we reduce the steel percentage. But that is not true, because with corrosion, we have a strong reduction in ductility in the rebars. And that ductility could, and that aspect could lead to a a strong reduction of ductility at sectional level and a structural level. We have two main corrosion that we can have in our reinforcement. Usually we define the uniform corrosion or the local corrosion that create pitting. Usually the uniform corrosion is related to carbonation of the concrete, a reduction of the pH, and so to mainly uniform corrosion. In case of chloride penetration, we can have pitting corrosion that could still more reduce the ductility. That are mainly the typical reaction, degradation that we have in the reinforcement, and mainly in corrosion with chloride, we have this pitting that could create a further reduction that is uniform corrosion. This is pitting corrosion. Anyway, that is usually uniform corrosion, pitting corrosion. You can appreciate how we can have a reduction of the strength, a reduction of ductility, that are mass loss in percentage of the rebars. Not only for pitting corrosion, but also for uniform corrosion. So starting from that assumption, that discussion that we had in the community, in new model code, we define some relationship for modeling the corroded rebars. And in particular, all is referred to a mass loss, so a reduction of the mass of our rebars. That is worse because a lot of data that we are using for validating that model was related to tests in which the degradation is modeled as a mass loss. And in particular, we can see that we can reduce the force in the bar, the strength of the bar, the yielding strength and ultimate strength with this correlation with the mass loss and a coefficient that is alpha. Whereas we can also define the ultimate strain with this other correlation with here we have the mass loss and the beta value. Here is the value given in the model code for that is the reduction of yielding strength, ultimate strain, and ultimate deformation with uniform corrosion and pitting corrosion. That relationship were presented in model code came from several tests and several papers in the literature. One of the first that considered especially not only the strength degradation, but also the reduction of ultimate deformation in that. And if you see from that paper how the alpha and beta are very close to what was presented in model code for yielding, ultimate and ultimate strain and deformation. That model was validated considering a lot of tests available in the literature. But that tests were made on single bars. There are a lot of literature on testing of different bars. The mass loss was measured, and the ultimate strain, yielding strain, and ultimate strain is given. But when we model, when we apply a new model, we have to consider also the effect at structural level. Not only that is validated, the validation is made at material level, that it means the rebars, but the validation should be made also at structural level. So we start an activity taking a lot of data in the literature. That are the tests that I presented in this conference, and you can see how the experimental result and the capacity, the yielding capacity of the beam and the ultimate capacity of the beam fitted well with the model presented in model code, but not only with my test, but a lot of tests available in the literature recently published that are tests published in 2021 that are other tests published in 2023. We are still gathering information and validating that model with all data that we can able in the literature. So the model seems to fit and to work very well, not at structural level, modeling at structural level. That is very important, but something goes wrong. That is the situation of some tests performed in 2022, because the problem is sometimes that you check the result, and you can't take all the results in a database without having a critical analysis of the result. In that case, they perform a very strange accelerated corrosion that give a more uniform corrosion instead some localized peak, only one peak. So probably there was some wrong in performing not a natural corrosion, but was an artificial corrosion. So that was some wrong, but I think that was some wrong because it's not usual in existing structure to have one pitting or that situation. But still we discussed and we found that only reducing the ultimate corrosion to the elastic one, we still have a good result. That is long to explain, but because it's pitting, one pit tends to localize, and the definition of the mass loss probably is not so good. So I go to the conclusion, and I think that we can, I think, have in existing structure we have this new aspect. I think very important the definition of partial factor, because for the design, I think the model of degradation is very important, because before this document, really the idea to consider the degradation only as a reduction area is not a problem also of ductility, but if you go also a sectional analysis, we can have very different results. So thank you for your attention.
Thank you very much. You introduced the topic of assessment, and again, Alberto was involved in the development. All the questions and more lunch break. You know, we have very intensive program, and we will continue with assessment, because that's something that was mentioned already a couple of times in different presentations on existing structures. We can have information, and how we assess that information and how we handle that information. Sylvia Kessler. Sylvia is also convener of the task group that is dedicated to monitoring. So please, Sylvia, help us.
Okay, thank you very much. So I already know that we are probably very much out of time, so I try my best that you do not want to miss your lunch break. But have a look also on the assessment of existing structure. We already heard a little bit of it. But first, I would like also to acknowledge my major colleagues. There's a large group behind all the results which we are showing, or which are in the model code. But here's the most important one, my co-convener, Maria Pina Limongello from Politecnico di Milano, as well as Eftichia Apollistidis. She's our technical secretary and very active. And last but not least, also Alfred Straut, which is a convener of the Commission 3 in general. And I think this is a very important step forward in the Model Code 2020, that now we are also dealing with the existing concrete structures, because mainly we are trained to design new structures. When I studied civil engineering, I could calculate every kind of model like an ill monkey. I was trained really like a monkey, but nobody told me what to do with existing concrete structures. And this is definitely something which we should need to have a further look on it later. So the use phase and also the repair phase is very, very important. And you can see here that all the task groups which are related to the existing concrete structures. You just heard a talk from Alberto Meda, he was involved in the task group 3.2 modeling of structural performance. But now I would like to give you a short flavor of what we are doing in the task group 3.3, life management, testing, and structural health monitoring. And where do you contribute to the Model Code 2020? So we have two major chapters where our results went into it. The first one is the chapter 3011, verification of structural performance assisted by testing and monitoring. You can see that this chapter is very, very long, and I can tell you we tried really to condense what's all in it. And we contributed to the chapter on conservation, which is now the chapter 38, which is, I think, if I think correctly, it's the last chapter of the model code. It seems to be very, very short, knowing what kind of tasks are behind that, and hope that this is probably also something which we have to evaluate further in the next future. So we, in order to get started to our contributions to the model code, we prepared a special issue, which you can find in our journal from the FIB, the Structural Concrete. It was released in 2020. This was our starting point. And we were fast enough in order to already release our background document. So I invite you to have a look on the Bulletin 109, and I show you some of our results from the Bulletin 109. It was on the booth from the FIB, but it was sold, so please have a look online. And currently we are also preparing a next special issue in the Structural Concrete, hopefully to be released at the end of this year, at the beginning of next year. But nevertheless, here we are talking about testing, structural health monitoring of existing concrete structures. And now I show you something which you will probably see in the next future from every German. This is now our most famous bridge. You can see that existing is still in parentheses. It's not existing anymore. And if I would ask you, if you would have been in charge of this kind of bridge, what would you have done for inspection, for monitoring, and for decision making? And I would assume they will get totally different answers from every one of you, even though we are civil engineers and it's our major task in order to maintain our existing structure. So, but what are the main questions behind that? So what is the critical defect here? What we should really have a look on it. Which is the non-destructive testing, or which is the structural health monitoring methods which you would have been applied? What would have been here the right solution in order to prevent this kind of failure? And we are happy that we had no injuries at all, because this happened at 3 o'clock at night. I would also get totally different answers from all of you if I would have asked you what are the models suitable in order to assess the structure and in order to make the performance prediction of this kind of structure. And probably all of us, we would have come to a different conclusion, to a totally different decision what to do with this kind of structures. The fun fact is this is a bridge with 3 structures in total. The other 2 parts have already been repaired. The part which failed was scheduled for repair for the next summer. So we were already too late. If you have now a further look on the condition over the time, we normally have a designed service life at the end. We know we have to fulfill a minimum requirement on our structures. And at the beginning, even so, we have a lot of models. The condition performance could look like this, could look like this, could look like this, because the execution has also a huge effect on what we have designed. And we know that. That's the reason why we do need inspection, also because we have ongoing loading and ongoing environmental effects on the bridge, and we need frequency inspections. Probably in every country it's scheduled a little bit differently. At least in Germany, you have to look every 3 years to any kind of infrastructure. And besides all the inspection methods you can apply, so we have also a bunch of different monitoring, and we have totally different questions we have to answer then. So what is the, when should the structure be inspected? What is the objective of the inspection? We would probably always look on totally or some different spots on the structure, which are the parameters of interest, because we also have to check that we measure or indicate for these kind of parameters, which we can easily use later on for the condition assessment and for the performance prediction. Why do we should measure a parameter which you cannot work with afterwards, even though it's most often the case? So which methods can be applied? I already asked these kind of questions. And what we never ask ourselves, are these methods reliable? Because you can buy a bunch of testing equipment for reinforced concrete structures, but is this really necessary? We do not know that. But coming back to the condition over time, normally we have our first inspection, and then the curve could look like this. So we are happy. So the execution was much, much better than we expected. This could happen, but it could also happen otherwise. And here, a very simple example why it could also look very much worse than we expected during the design. Here I showed a very simple example. especially for structures which are exposed to chlorides with wetting and drying, where we have to be concerned about chloride-induced corrosion. Here I have the reliability over time, and I made the calculation based on the current code, which is in line in Germany right now. I checked what are the worst exposure conditions in Germany, and I compared this with the minimal material resistances which are required, and I checked what is the minimum exposure conditions where we have only a few chlorides applied on our structures with the highest material resistance which I could use according to the codes. And then you are surprised to see that we have a huge variety. And if you're not now very well related to what means here the reliability, and I marked here the line with the reliability beta of 0.3, this means that there we have a 10% of corrosion. A 10% probability of corrosion. This is what's now allowed in Germany to build. So you have a really high probability after 20 years of corrosion. Reliability of 0 means 50% of corrosion probability. That's the way how we are constructing nowadays in Germany, probably also in other countries. We hope that the lab performance concept will bring us here a step forward. So we really need to be concerned that our condition over time will look like the red curve we see on the left-hand side. But nevertheless, we should also take the advantage that we can use inspection, that we can use monitoring, and mostly, as is probably in most countries, we apply it when we have already a certain damage or we have a certain concern about the structure in general. And here I quote the head of the rehabilitation of the Federal Highway Administration in Germany. For them, monitoring is a palliative measure. But nevertheless, I hope that we can also use this in a positive way. And if you apply on a certain age monitoring, I think that is also a very good methodology in order to extend our remaining service life. We all know that we cannot rebuild our infrastructure, even so they have probably mostly reached their design service life. So we need to find measures in order to extend the service life. And here I would like to invite you to have a look in the Bulletin 109, which gives you here some tools in order to do so. And the bulletin is structured as follows. So first we have a chapter compiling on the different condition surveys from testing and structural health monitoring. We have the methodologies for condition assessment and performance prediction, including all the data which you have derived beforehand from the condition survey. And we rounded up with a decision-making process, so what can you really do? And last but not least, we added a lot of case studies in order that you get an idea in which kind of situation you can apply a certain inspection or a certain monitoring methodology. And now here I give you a very short overview about each chapter. Here, for example, the chapter on the condition survey. You see here the observations of the technologies. Now it's not really good working. Then how do you plan and execute it? What kind of testing data? Where do you test the data? How many data you should collect it? And how do you can also do a kind of data quality checking regarding measurement uncertainty and so on. And here you get a lot of tables, what to do in case of the damage or deterioration processes you're expecting on your structures. You can also have here further insight about the condition assessment. If you now have collected all your data, how you can transform it into indicators, what kinds of models you can apply in order to get a damage indicator, in order to get an information about the updated key performance indicators of your bridges. And you have several methodologies here available, like time frequency methods, time series methods, model-based methodologies. And we have here a bunch of different tools available, and I hope that we will much more use them also in the future. And this bulletin gives you a nice overview under which circumstances, which methodology is the best to apply to. And I already mentioned we really need to check what we are looking for and what are the quality of our data. And what are the indicators of our data quality? If you consider that we can also have a probability of a false alarm, that you detect a defect, even there's none, but probably this is not such a big issue in our case. For us, it's much more important that we have a certain probability of detection for our defects, which are critical. Then afterwards, we also need to know, are we able to localize a defect? Do we know the correct size of the defect? I think that's for most of the defects we are mostly looking for. You have no idea about that. And this is something which we attribute to the testing uncertainty. And if you also include the probability of correct sizing, then you have the measurement uncertainty. But even so, we do know now what kind of defect we have, what is the size, what is the shape, what is the location of the defect. We also need to know what is the criticality of the defect. And then we are able to calculate the probability of failure. And this is something what probably not have been done at our bridge in Dresden. So furthermore, when it comes now to the performance prediction, when we have an idea about the quality of our data and also of the model uncertainty, we can apply a lot of different models for the performance prediction, starting from physical-based methodologies to statistical-based, stochastic-based, and data-driven-based models. So once again, we have a lot of different methodologies here available, and we do know that we do not have for any kind of iteration process here physics-based models, unfortunately, and then we have to check which model is the most suitable for our case. And here, once again, you see the transformation into the performance indicators and key performance indicators. There's still a lot of research being done, probably also here in Australia and New Zealand. And in Europe, we are trying to get here that we find a common agreement on our key performance indicators. And last but not least, we have the decision making. So what do you do now with your information? If you're an assets owner, if you're a user, if you're a constructor, you probably come up to a totally different decision. But we need to support our decisions that they're made based on our indicators and to bring them, to make a equally based decision, keeping in mind not only the cost, perhaps also the sustainability. And for sure, we cannot sacrifice safety or reliability. That's out of question, but we should check our costs and our sustainability. As I already mentioned, we included a lot of different case studies, starting with a short description, what was the motivation in order to apply different testing or structural health monitoring techniques, the data description, the analysis procedure, as well as the performance indicator. And every case study has just one single page, but we added as well the references that you can have a further look. And we have references from here just from a multi-story building, as well from several bridges, from wind energy, from dams, from whatever you can imagine. We have different case study in order to give you an idea what you can do for your structure as well. And so something, as I already mentioned, what you can find here in the bulletin 109. And I also invite you, if you're interested in this kind of topics, please write me an email. You're more than welcome to be a member also in the task group 3.3, because we still have a lot of work to do. And in the very near future, we would like to focus on the following subjects, especially on the extension of the service life, which I already mentioned before, but I think this is one of the clues in order to increase the sustainability of our infrastructure. So what can we really use on energy and structural health monitoring in order to extend the remaining service life of our structures? What kind of new technologies are out there which we can develop further? And we know there's a lot of robotics, a lot of drones, a lot of self-sensing monitoring, and they're probably not all suitable, but we need to check and to identify which can really bring a benefit to our assessment procedure. Data management analysis. I have a huge project going on. We are collecting more than 1 gigabyte of data from monitoring every week. So we really need artificial intelligence to deal with our data amount, and we know that no one can do it by hand. Here we need more support, and we also need to be aware what kind of uncertainty we are including through the artificial intelligence and our modeling. We already discussed it, the decision making. I hope that we can include it in future also in the kind of digital models, which assist us immediately to bring all the data together which we need in order to be able to make the decision making, because we still want to be the human involved. So we want to be the human in the loop when it comes to digitalization, not on the loop. We as engineers should still take the decision, as at least our thinking. And last but not least, how we can also contribute to increase the sustainability of our already existing infrastructure. And if you feel now, okay, this is a topic where we would like to contribute to, please come forward and contact me. So.
Thank you, Sylvia. Excellent, because you also also give this open invitation to participate, and as we have already heard, service life extension and sustainability cannot be separated. So you have the best person to talk to if you are interested in life cycle management, condition assessment, and data-informed assessment. And no, we will not go, please, yet to the lunch break, because we have a very important last presentation that is about practical application of all that you have seen. So bear with us for a moment, and Akio will tell you how you design sustainable bridge structures. Yes?
Thank you,
Please.
I'm a last presenter, but please be patient a little bit, because my presentation is from the practical side. So I'm focused on the last part of the model code, especially the chapter 34, decision making. It is not so easy to show the very, very good example. But today I try to show you some parts and some clue in the near future. One is a Mio viaduct, another is a Lincoln viaduct in the United States. So these photos come from Davis. Thank you very much. So everybody well known in this is the bridge of the Mio in France. And my calculation is very, very rough, because the information is very limited from the internet. So the project cost, when we get the project cost, roughly the CO2 emission is not easily calculated, but it is very rough. So the cost is about 400 million, and I always use 400 ton per million euro. So this is the indicator, my indicator in developed countries, and the developing countries almost double, 2.5 times. But I use this calculation 400. And also finally, the total CO2 emission estimated about 160,000, or from the material, it also 165,000. So this is roughly very, very close to the real. And there is and this is a very high level viaduct, as you know. The highest pier is 250 meters. So before that, the truck go down and go up. So I estimated that the past load inclination is about 5%. The length of the road in the past was about 10 kilometers, and also the now new viaduct is shortened to 2.5. So the past vehicle speed is estimated by 10 kilo, and also now it's about highway. So compare with past road, the reduction of the CO2 is about 0.011 per truck. So this every data is come from the German research, and there is another data from the October 2016 to the June 2017. There are 160,000 vehicles, mainly a truck. So the per day, 890 trucks passed on this viaduct, which means the 890 multiplied by 0.011 means 10 tons per day. So it's a saving of the CO2 emission. Finally, the CO2 emission due to the construction divided by this value, which means 44 years. So after 44 years, roughly saying the construction emitted CO2 compensates zero. So 40 years is not so long compared with the CO2 absorption by the concrete in this bridge. So this kind of estimation in design process is going to be the very important issue in the near future when the designer and the client do some decision making in the design process. So second one is Lincoln Viaduct in the United States, North Carolina. This is very beautiful bridge located in the national park. So at that time, the owner, should say the construction company, and it's a penalty, the $1,000 if the cutting the one trees. So it's not so small money. So finally, the designer and the contractor selected everything constructed by over the bridge, piers and also the girders like this. And I estimated this situation again. So this is a very rough calculation in temporary jetty and also the highway. The jetties emit CO2 about 48, and also the viaduct emit CO2 about 376. So if these trees are Seda, I don't know the real situation, but assuming the Seda, the per year 0.8 tons CO2 are absorbed by trees. So the in 100 years service life going to be the 80 tons, and also if the tree cut, and the loss of the CO2 is about 24, because it takes 24 years to be grown up on the tree. So finally, if the contractor cut the trees, 56 tons CO2 would be the 100 years absorption of the CO2. And compare with conventional way and number one, and also the special construction, real construction number two, the difference is like 72 tons. It's a 20%. And also, if the CO2 credit is €140, it is going to be like this. So the 56 trees multiplied by the 1,000 penalty, it's going to be the €780. So compare with 140 and 780, it's about 5.6 times. So I would say this money is not so small for the contractor. So the 90% different from the cutting tree, and also the use of this special construction method. So it's the $1,000 penalty is a good level to choose to preserve the trees. So this kind of the pre-calculation in the design process will be needed in the near future. So we are thinking about the three pillars is eco, like this, but I found a very, very interesting proposal, and it is nature positive. The environment, including another two kind of aspects. So we must recognize that economy and society built on the environment. And nature positive could have significant influence in the process of the decision making, and it might be. But I think this is a very interesting proposal. And the carbon neutrality is mainly focused on the economy and society, because human life. And also the nature positive is including all of them. So we have to think about this proposal. And this is proposed by the Stockholm University. They call it SDGs wedding cake. Our society, our economy, they are built on the very big environmental basement. And also that they had another party, it's a nature positive, 30 by 30. By the 2030, we preserve 30% of the land and the sea, and before the 2020 level. And also we have to reduce the endangered species. So this is the philosophy of nature positive. And this is a real data by the network for greening the financial system, the financial sector. Our work, highway and rails and trucks, and also the construction, these activity affect the environment very, very, very much. Risk rating is very high. We have to think about this too. And nature positive for the bridge's future, we have to think about a viaduct that is more eco-friendly than the embankment. This is the planning process. And reduce the use of the wooden formwork. This is a construction company's issue as much as possible. Because so we should limit it to the use of the traceable timber. Otherwise, we use a steel formwork or fiber plastic something. So that we have to avoid the use of timber. And single-span bridge over the valley by using a suspension structure or a launching. This is very important to preserve the beneath the bridge environment. And also cantilever or span by span rather than the horseback walking construction. So this kind of issues should be rising, and not only the economical reason, but also the environmental reason. And let me show you another issue. The one is water, another is sand for the concrete. Both material is very, very important. And we should know that people in the world who cannot access the clean water is about 2.1 billion. And think about the Roman concrete, the part of Roman concrete, they use seawater because the Roman concrete is no reinforcement. But now we have a plastic fiber technologies. In this case, we can mix the concrete by the seawater. And also sand. This is very huge amount of sand. For example, 10-meter high, 10-meter wide, this wall built on the equator. So lots of sand is used year by year by the concrete. And in order to avoid this issue, it is a very, very small amount, but we sometimes use slag sand, or we use the dune sand instead of the normal sand, the concrete. Okay, let me mention about this. I show you in the Sydney last week. This is a roadmap of GCCA, and red part is down by the supply side, like us. The GCCA said it's 42%, so many. But I think about that. Our society is for the structural concrete. The structural concrete used about 60% cement. So multiply 60% is about 25%, but 0.4 gigaton is still a large number. And this is a Japanese examples. And here is a non-clinker cement. It's about 20% contribution. And also, this is a demand side, about 20%, roughly the equal as GCCA's roadmap. But most important thing is material efficiency design. So many colleagues mentioned about this. And also more intentional use of the structure, and also life extension. So soon our roadmap will be introduced, launched in the society. By using this 20%, about 0.4 gigaton, we try to. It is a big challenge where to reduce by using this kind of treatment in the future. Okay, I'm from the private company. I'll show you the situation now, because the FIB's society from academia, from the owner, from the supplier, and also the construction company. Important thing is this is an issue for the private company because the Finance Institute pushed us to show the Scope 3 data. And because the Finance Institute has also pushed by the BIS. BIS is bank of the bank, central bank of the country. So in the near future, we have to disclose the Scope 3 data, but important thing is construction company didn't know the maintenance process. So if the FIB can do that, and especially the task group 10.2, we have to show the standard maintenance scenario in a different durability level, standard level and the high level and the super high level something. So this is important for us to show the Scope 3 data to the Finance Institute. And this is my question myself. Should our optimization consider the priority for environment and also society and economy something? Please think about, and I ask Agnieszka to take into account in the activity of TG 10.2 like this. Okay, so in order to prevent the environment, which is the foundation of our society and economy, FIB needs to show the optimal path for decision making regarding sustainability. Sustainability decision making not so easy, but we have to do that. Okay, so we can live the very convenient, but we recognize the human is only one creature on Earth to increasing entropy. So this is the message from the Earth, I think. Thank you for your attention.
Thank you, Akio. Akio was our last speaker and very strongly involved in all that we have been doing in the past for preparing the FIB strategy for the future. I know that we took much more of your time than intended. I hope you don't regret staying here. Most of the speakers are still present, so please take your time and engage in conversation. Yeah, and I hope that inspires for finding your dedicated spot within the full spectrum of what we are doing. So by this, the session is closed, and thank you very much for being here.